work that we did over the last couple of years in collaboration with people from Switzerland, but also from the US and especially also from France, which I will get into more detail. So during this week, we have seen many different effects or physical effects that arise from different kinds of spontaneous symmetry breaking, be it magnetism, superconductivity, or ferroelectricity, or also ferroelasticity, which we haven't seen so much about yet. And of course, we can kind of look at these at electronic symmetries that can be broken, or structural symmetries that can be broken, even though it's clear that in most cases the two are coupled. In this talk, I want to focus more on structural symmetries. So whenever there's a spontaneous breaking of a crystal symmetry in a material. And in particular, I want to focus on collective phonon modes that are remnants of broken symmetries. So if you have a structural phase transition, it means we have a material that goes from a high symmetry phase with the space group G. At a certain temperature, there's like a breaking of symmetry. There's some motion of the atoms, which we assign an order parameter n to, which brings the system into a lower symmetry. And if we from it is correct. Yes, of course. Excuse me for that. Yes, and we can kind of assign an order parameter, which I call here eta, which we can correspond to the motion of the different atoms. If we expand this in terms of Landau free energy, we can assume the free energy that we expand as a function of the order parameter, where in the typical first order Landau approach, only the first parameter is temperature dependent, and this will turn the single well above Tc to a double well below Tc. Now, in solid state physics, there's this kind of idea of the phononic soft mode, which is if I have this energy landscape, there is kind of a phonon that has the same displacement pattern as the displacement that brings us from the high to the low symmetry, and kind of the frequency of this phonon corresponds to the square root of the curvature of the free energy. So if I'm above Tc, I have a frequency. That means that I have a phonon that is corresponding to the curvature of my free energy. So if I kind of go closer to the phase transition, the frequency, the curvature will decrease, the frequency of this phonon will go down. At Tc, it will go to 0. And then below Tc, the frequency of this phonon will increase again, but instead of around an order parameter value of 0, we will start kind of vibrating around one of the minima of the free energy. Now, this is kind of if I have a single mode. What if I have a distortion that has a multi-component order parameter? In terms of phonons, we can think about this as there is like a doubly degenerate phonon that becomes soft. If we do the free energy expansion, what we find is actually that in the quadratic term, so in the curvature, there is nothing that breaks the anisotropy. It's only higher order terms that will break the anisotropy. So that means that even if we go from a discrete space group to a discrete space group, we can have kind of something that looks like the spontaneous breaking of a continuous symmetry. So basically the discreteness of the different phases is kind of irrelevant at Tc, which people sometimes call dangerous irrelevance. Now, we know that if we break an n-dimensional continuous symmetry, we get kind of modes that correspond to an amplitude mode, which people call the Higgs mode, and n-1 massless modes, which correspond, so one corresponds to climbing up the head, one corresponds to going around the head. So we get basically one amplitude and n-1 phase or Goldstone modes. Now, the question we pose to ourselves, so this is well known from magnetism or superconductivity, but can we kind of find an equivalent in structural phase transitions and with that in phonons? So the tool we used is density functional theory, which is kind of a numerical way to solve the many-body Hamiltonian by, instead of considering each electron as its own particle, we kind of consider just the electron density, which allows us to kind of calculate ab initio properties of materials. Especially, we're able to calculate, for example, forces between atoms and energies, which allows us to calculate, for example, energy landscapes as function of order parameters, but also phonon frequencies. Yes? So exactly, the constraint is kind of on choosing the symmetry of your high symmetry. So I will go into it actually on the next slide here. So basically what we do is we kind of start with the high symmetry cell, and we can calculate the phonon spectrum. Now, if the system has any instability, this will show up as kind of frequencies that are imaginary. Now, the idea is that the frequencies that are imaginary, these are kind of what we are going to use as our order parameters. And we can then kind of reduce ourselves to the subspace of these unstable modes and derive the lambda polynomial, taking into account all the symmetry constraints of the different modes that are involved. Then further, we take the second derivative of the free energy of kind of the high symmetry phase, but then we plug in kind of the unharmonicity coming from the terms from the soft mode, which kind of, because it's constrained by symmetry, this gives us kind of one reduced block in this matrix, which is unharmonic, and we have all of the rest of the phonons, which we consider to be independent of temperature. Now we applied this to a system that we know has very low unharmonicity, because the energy landscape corresponds of a tilt. So this is hexagonal rare earth manganites. They have this kind of octahedral, not octahedral, but bipyramidal tilt. If we calculate the free energy, so this is actually done by Serguei. I don't know if he's here. Yeah, he's here. So we get like kind of an energy landscape that is very flat. It has 6 minima, but the 6 minima, they only start playing a role lower. So we were asking ourselves, so what about the phonons? If you look at the phonons, we see as a function of temperature, we kind of see that, okay, we have here this doubly degenerate branch, and then this splits into a amplitude-like mode and a Goldstone-like phonon mode. So what we show is kind of, okay, there is kind of, in the phonon spectrum, we can find a signature of these Higgs and Goldstone modes. Then, together with Dirk, also from University of Geneva, we were doing Raman, and we kind of compared our calculations, and we found that, okay, we could identify this first A1 mode as kind of the Higgs phonon mode in our system. The Goldstone, unfortunately, is not visible by Raman because it has the wrong symmetry. Okay, so motivated by this, we were working with James and Mike, and we were looking at kind of an even more complex system, but very interesting system, which is this pyrochlor cadmium niobate. And in cadmium niobate, what is very interesting is that there's 2 different modes that are soft. And moreover than that, these 2 modes, both are multidimensional, plus they have almost exactly the same energy landscape. So if I look here, we see that the blue mode and the red mode are the 2 different modes, so they lead to almost exactly the same energy lowering. In addition, we can see that there's a red line and there's a like a pointed line, and there's a line, and we see that these have basically almost these lead to almost exactly the same energy lowering. So we really have kind of the superposition of two Mexican heads. Now, we did the whole Landau theory. We did derive the whole Landau theory, and we kind of noticed that, okay, what we get is something that is known from two-band superconductor, which was actually like put forward by Tony Leggett in 1966. That is, we get kind of a phononic analog to the Leggett mode, which is a mode that couples basically the two order parameters. So if we look at the symmetry breaking, we get again kind of a phonon mode that corresponds to the soft mode, and it breaks into a Higgs and the Leggett mode and the Goldstone modes, which we did not plot here. Okay, so you might say, okay, this is all nice, but is it really important? Well, it can be, because from this we get kind of phonon modes that correspond directly to the lattice distortions in our material. So we can use this, for example, using terahertz radiation. So the idea would be, can we kind of control the phase of a material by pumping the Higgs mode using terahertz? So what we can do is we can use these Landau type equations that we have, and we can kind of build. Okay, now this one is also that. Okay, we can kind of build the phononic equations of motion, and we show that indeed, because the Higgs mode is a Raman active, we are able to kind of pump the Higgs mode and which leads to a energy transfer to the Goldstone mode, which in principle could lead to a phase control through terahertz radiation. However, by now we were not able to propose a mechanism to really kind of directly, like deterministically change from one phase to the next. Okay, so far to these modes. Now I quickly want to take some time to show you this new method we developed to actually calculate fully ab initio the phonon frequencies at finite temperature in a material. So basically, if I think of phonons, I can of course just calculate the phonons by taking the second derivative of the total energy. However, if I think of a real system, the atoms are actually not sitting in a place, but each of the atoms is moving around because they're moving because they are kind of activated by different phonons in the material. And the more phonons are active in the material, the more the atoms are moving, and the more they are also interacting with each other. So the method we developed is that we first calculate the phonons, then we calculate how many phonons of these are active, and then we kind of displace all our atoms to get kind of an effective type of phonon. So this is called quantum self-consistent ab initio lattice dynamics. It's a code written in Python, but works together with our first principles programs. It's freely available, and it's also compatible with other methods like ALMA BTE for thermal transport. So, okay, so in principle, how it works, so as I said, we start with a simple set of phonons. We calculate the thermal displacement matrix, and then we create n different configurations where we displace all of the atoms according to the thermals, or quantum statistics. Then we take all these n different configurations, and we find the phonons, force constant that fit best, and we recalculate the phonons. And this creates a self-consistent cycle that allows us to calculate the the thermal influence on the phonon frequencies. Of course, so this is DFT. So when you create n configurations, this is super expensive because we need to make n supercells without symmetry because all the atoms are moved away from their position. So in order to overcome this bottleneck, we are using kind of a combination with machine learning potentials. And the idea of machine learning potentials is kind of that we use the training set of atomic positions and their corresponding energies, forces, and stresses to create an effective potential, to train an effective potential. And the effective potential combines the speed then of empirical potentials with the accuracy of DFT. Now the potentials that we are using are called moment tensor potentials, which kind of, on the contrary to the neural network potentials that are out there, kind of have a functional form that we can refer to, which corresponds to basis functions that look like this, so which have a radial part and also kind of an angular part, which allow us to fit a potential or to train a potential. And the way this is implemented in Q-scaled is actually using an active learning mechanism. So after we create our n thermal configurations, we calculate an extrapolation grade, which is kind of a measure how close is my current configurations to all the other configurations that is currently present in my training set. If this is smaller than a given threshold value, that means the machine learning potential should actually be good, which allows us to calculate the forces using machine learning. If we have something that is bigger than the threshold, which means our machine learning potential is probably extrapolating a lot, so this means we have probably not such an accurate fit, then we calculate automatically forces from DFT and we retrain our potential. So like that, you can basically start doing your calculation with this method, and on the fly, you're training your machine learning potentials. In the beginning, you will do mostly DFT, and in the end, everything will be done using the machine learning potential. Now, to show you how this works, I will show you our data on potassium tantalate. So potassium tantalate is a quantum paraelectric, which means it's something that is almost a ferroelectric, but not quite. It has a soft mode, which you see here. Oops. It has a soft mode, which you see here. So the frequency is decreasing and the dielectric constant is going up, but the phase transition would be below zero. But so it's not happening. Now we calculate this using our method. Now the interesting is, if we calculate the phonon band structure using DFT only, we find that there's an instability at gamma, which corresponds to this polar instability. Now, even if we use our method, so in our method we use thermal activation as well as the quantum motion of all the atoms. So even at 0K, the quantum motion is already enough to stabilize this unstable mode. And then if we increase the temperature, the frequency of this mode will go up and up. So we can really see really strong harmonic effects on this polar mode. Now if we compare to experiment, on the left you see the phonon frequency squared, calculated in blue, and experiment in red, so we can really be very accurate. Then on the right you see the dielectric constant, because the dielectric constant in potassium tantalate at really low temperature is really diverging, because the phonon mode is getting so soft, and the phonon mode is actually the main contribution to the dielectric constant. We find that, we find also this strong increase, but nothing is perfect, so we don't find really the extremely high divergence, but this is probably just because the phonon frequencies at the end, what we see, are not quite as low. Like there's, as you see on the left picture there, the measured ones are a bit lower than the ones we observe. Yeah. Okay, so the last thing I want to show you is our new implementation that we can actually do also relaxations at finite temperature. So I showed you the paraelectric phase, which works well, but of course, if you're in a ferroelectric, we know all ferroelectric are pyroelectric, so if you have different temperatures, the amplitude of the polar mode will be different. So in a way, if I have a double well, I don't know at the given temperature at which point of the double well is actually the minimum. So I might be in the minimum, but I might not. So we kind of adapted the workflow a little bit, that in addition to calculating kind of self-consistently the phonons at finite temperature, we also at each step extract a symmetrized average force. And this basically allows us to calculate at finite temperature the position of the atoms. So I show you here the cubic to tetragonal transition in strontium titanate. On the left, you see measurements. You see the phonon that is going down in frequency, and then it splits up in a low temperature Goldstone-like mode, a low frequency Goldstone-like mode, and an amplitude mode below 100 Kelvin. Now, we can calculate the same, and we find the temperature too high. This is because if you calculate with DFT, the distortion in strontium titanate, it comes out too big. This is why our TC comes out too big. But we see that the phonon below 300 Kelvin, we get a distortion from 0 that increases as a kind of with the typical order parameter shape. And also, if you look at the phonon frequencies, we find that above TC, we see the degeneracy, and then it splits up in a phase and an amplitude mode. So we can really, from first principles only, calculate the phonons and the phonon splitting at finite temperature. Yes, so that is my conclusion. So we can kind of describe soft modes using first principle calculations. We can either use some effective anharmonic models to describe their behavior at temperature, but we have this whole machinery that we actually now can calculate phonon frequencies at finite temperature using DFT plus machine learning. Thank you for your attention.